Now I'm going to discuss the so-called no-slip condition. And the no-slip condition is one of the strongest influences of viscosity that it has. It causes drag, as I'll discuss in a few minutes, and we'll discuss in more detail when we get to the very end of class. And the no-slip condition states that the tangential component of velocity is equal to the tangential velocity of the wall. So that is a sort of mathematical and abstract definition of it, but I think if I draw a picture, it will make a lot more sense. So here we have a so-called flat plate. Okay, and so this here is a flat plate. And we have a flow of, say, air flowing over this plate. And in front of the plate, the velocity profile is perfectly flat. It has some velocity cap U. Okay, get rid of that, put a cap U. Okay, so now as the fluid starts to go over the plate, the no-slip condition starts to take hold. So we have the n hat direction pointing up. And what the no-slip condition states is that at the wall, right there, at the wall, the tangential component of the velocity vector is equal to the velocity of the wall. So in other words, this plate is stationary, which means the tangential component of that the velocity of the plate here is exactly 0. So the no-slip condition states that the velocity tangential to the wall is equal to the tangential velocity of the wall at the wall. So since the wall is not moving, that means that when the flow starts to interact with the wall, the magnitude of this velocity here is 0, and the velocity profile no longer maintains this nice uniform profile. Instead, it starts to develop a shape that looks something like this, where we start to get a curve, where far away from the wall we start to recover the undisturbed velocity, but very close to the wall and at the wall the velocity is 0. So basically what this means is that the tangential component of the velocity at the wall is 0. Okay, and so that's the no-slip condition. It just means that the velocity in the direction of the surface, or the velocity that is trying to go across the surface is 0. Okay, and it just moves with the okay, and so basically that's what no-slip does. Is it just basically forces the velocity to be 0. And mathematically, this means that the tangential component, the tangential velocity of the fluid is equal to the tangential velocity of the wall. Okay, so that's basically how it is. Because this could be a plate that's instead of air flowing over a plate like this could be a plate moving through stationary air, like an airplane wing, or something like that. But the picture would look more or less the same. Okay, and so now what we and this will generalize that if the wall is stationary, then you can just say that the tangential component of the fluid is 0, but that's only if the wall is stationary. Okay? And what this does is, you can see what the no-slip is doing is it's introducing a velocity gradient near the wall. And now you have viscosity and a velocity gradient. That means this is going to induce a shear stress at the wall if there is a flow. Okay, and so now at the surface here we have a shear stress, tau, that is slowing the fluid down, but it's inducing a shear stress that is trying to basically move the plate forward like that. Okay, and what this does is this is a major component of drag forces on an airplane wing, and also pressure drop in pipes. So this no slip condition, in combination with viscosity, cause shear stresses, and those shear stresses are why you need pumps, why you need so much thrust for an airplane, things like that. Okay, and so this no slip condition is important, and we actually used it in the past without stating it, and we used it for the shear force example where we had two flat plates, basically a stationary plate on the bottom and a top plate that was moving at some velocity, cap U plate at the top. Okay, and we basically just stated that there was a linear velocity connecting the top plate to the bottom plate, and that the velocity of the fluid was 0 at the bottom plate and equal to U plate at the top plate. And so we had that U as a function of y equals cap U of the plate times y over h, where y is going up and h is the gap width. Well, if we look at that and evaluate it, we see that u is 0 on the bottom here, and u is equal to u plate at the top. And so this condition satisfies the no slip condition on both the top and bottom plates. And this scenario looks contrived, but in your car engine where you have thin oil-filled bearings, this is a typical picture of something that you'd see in a bearing in a car. So for those of you who go work in tribology and you work with developing lubricants, this is a very common picture that you will see. Now, sometimes you can get away with neglecting viscosity, and if you neglect viscosity, that is, you just pretend that it's 0. It's not actually 0. You're just pretending that it's 0 or assuming that it's 0. And basically what that says is that the viscous effects are going to be negligible. And if you can neglect viscous effects, the flow is said to be inviscid, and no slip does not hold. Okay? And so, and we will be dealing with inviscid flows actually later on in class because they're a lot easier to analyze. But now what causes no slip? Well, at the molecular level, we can zoom into a surface here. So I could sort of zoom in, and this would be a picture at the surface right here. And even at the molecular level, the surface of a solid is all craggy, like that. And if you consider that there is air flowing over this, well, air is comprised of a bunch of gas molecules that are sort of moving with a bulk motion, but there is there are a bunch of little random collisions, and some of those collisions knock and push some of the other molecules into these little valleys, and these molecules that are in the valley sort of get stuck, and they sort of stay there, and they appear to be stuck to the wall. So that means that a layer of molecules here is not moving. Then, if you zoom up, if you think about, well, then what's going to happen to the second layer of molecules? Well, this molecule here is going to hit this one, but basically this molecule here is not going to quite stop, but it will slow down substantially. And so a second layer of molecules will be moving far slower than the free-streaming molecules above, but still faster than the molecules below it. So essentially, then what this means is that the no slip condition is just caused by the interaction of a molecule with the sort of peaks and valleys of a surface at the molecular level, and you can't polish it. You cannot polish a surface to get rid of the no slip condition, because even at the molecular level, a solid is nothing more than a bunch of little molecules where you can sort of think of them as being connected together by springs like this. But even at the molecular level, there are still little peaks and valleys because a gas molecule can basically sort of strike there, and then it'll basically get stuck. Okay. So again, all this phenomena occurs at the molecular level, but it can cause global macroscale effects. If we could get rid of the no slip condition, planes could be much more efficient and things like that. But unfortunately, that's not the case. So, and the other condition that I'll discuss, it's called the impermeable wall condition. This one is a bit more intuitive, and you guys are probably familiar with it. And the impermeable wall condition states that the fluid does not go through a surface. Okay, and so that is, if I have a little picture here where I have a jet of water and it is impacting a plate right here. Okay, well, you know from experience where as a kid you had a water hose and you shot, and you're like playing with it, in some sort of water fight with your friends growing up, and they would normally get some sort of garbage can lid or something like that to defend themselves like a shield. Well, what would happen, you would shoot the garden hose, and that sort of spray or jet of water, it's called, would basically go impinge on the plate and then turn and basically go spraying out to the side. Well, the reason it goes spraying out to the side is because of the impermeable wall condition. That is, the flow of water is not going through this. It is not going through this flat plate. It is being stopped. So now that is not the action of viscosity. Viscosity is not causing that fluid to stop. Instead, it's just basically the gas molecules cannot penetrate through the solid, which makes complete and utter sense. Okay, and that is not the action of viscosity, is basically what's causing that. Okay, and mathematically, what this means is that the normal component of the fluid velocity is equal to the normal component of the velocity of the surface. So basically, if this plate here is stationary, that means whatever fluid velocity we have here, the normal component at the wall here is 0. Okay, which basically means there is no material, there is no gas or fluid basically crossing through the plate. And that's the same here as it is here. And basically that is why the flow is forced to turn and then follow the surface of the plate like that. And that's why it goes spraying out to the side, which you've seen in your everyday life. And in a mathematical form, at the surface, the normal component of the fluid velocity, which is this v dot n hat, actually get rid of the over arrow here, is equal to the normal component of the velocity of the solid. Because you could think of, in your water wars you had as a kid, if you were holding the garbage can lid, you would basically move forward, basically towards your friend, and now that plate is now moving, and basically that means that the normal component of the fluid velocity is equal to the velocity of the plate. Okay, is basically what that means. However, if the plate's stationary, this basically means that the normal component of the velocity is 0. Okay. So it's just a special case of this more general case. Okay? And it's not, and just we'll make a note that the impermeable wall condition does not hold for porous material, like a filter or sand or things like that. Basically, because basically for those materials there will be some portion of the flow that will basically go through the surface if it is porous. Okay, we will not be analyzing porous materials in this class. Those get kind of complicated. But yeah, and then finally, if you have both no slip and impermeable wall conditions, then the fluid velocity at the wall is just equal to the velocity of the wall, or if the wall is stationary, you can just make the blanket statement that the fluid velocity is 0. That is, you don't need to break it into tangential and normal components. You can just say, because the impermeable wall condition will state that the normal component is 0 if it's stationary, and the no slip condition will state that the tangential component of the velocity is 0 at the wall, and if you add them both up, that basically means that the total component of the velocity is 0 at the wall. If the wall is stationary, and if both no slip and the impermeable wall conditions both hold.